Okay, so let's continue with our discussion on geometric and algebraic multiplicity. Let's prove a lemma. If gamma is a geometric multiplicity of A and alpha is the algebraic multiplicity of A, gamma geometric, alpha algebraic, then the gamma is less than or equal to alpha. The geometric multiplicity of an eigenvalue is always less than or equal to the algebraic multiplicity of an eigenvalue. Now, by the simple observation made above, there is no harm in assuming that lambda is 0. So without loss of generality, we are going to assume that lambda is 0. So geometric multiplicity of 0 is by definition nullity of A minus lambda I, but lambda is assumed to be 0. So geometric multiplicity of 0 is the nullity of A. We have to show that if the nullity of a matrix is K, then suppose we show that if the nullity of a matrix is K, then x to the power K divides the characteristic polynomial. If we succeed in showing this, that means that the characteristic polynomial of A will have x to the power K as a factor, and this factor is repeated at least K fold. That means that 0 will be a root, at least a K fold root. So what is it that we are going to prove? We are going to prove this sentence. We have to show that if the nullity of A is K, then x to the power K divides the characteristic polynomial of A. Because if I show x to the power K divides the characteristic polynomial of A, that means that 0 is at least a K fold root. In other words, the algebraic multiplicity of 0 seen as a root of the characteristic polynomial of A has multiplicity at least K. So that's what you're supposed to show. Well, let us recall what is the coefficient of x to the power 0? What is the coefficient of x to the power 1? What is the coefficient of x to the power 2? We have to show that when will x to the power k divide the characteristic polynomial of A? When will x divide a polynomial? X will divide a polynomial if there is no constant term. X squared will divide a polynomial if there is no constant term and there is no x term. So x to the power k will divide the characteristic polynomial of A precisely when coefficient of x to the power 0, coefficient of x to the power 1, ... coefficient of x to the power k minus 1, all of them vanish in the characteristic equation. But what are these coefficients? What is the coefficient of x to the power 0? The determinant of matrix. Remember? And I know that the determinant of matrix is 0 because 0 is an eigenvalue. So surely the coefficient of x to the power 0 vanishes. What about the coefficient of x to the power 1? The coefficient of x to the power 1, remember, is minus 1 to the power n minus 1 times the sum of the n minus 1 by n minus 1 principal minors. Sum of the n minus 1 by n minus 1 principal minors. Now, the rank of the matrix, the nullity of the matrix is K. So the rank of the matrix is n minus K. Remember? Suppose, for example, you know that the nullity of the matrix is 2. The nullity of the matrix is 2, then the rank of the matrix will be n minus 2, right? The rank of the matrix is n minus 2. That means all n minus 1 by n minus 1 subdeterminants must be 0. In particular, the principal minors of size n minus 1 by n minus 1 are 0. Therefore, the coefficient of x to the power 1 must be 0, etc. Please complete the argument systematically. Okay. Now let's take up a simple example. Let us look at the example A0. The matrix is called capital A0. A1 squared, A1, A2, ... A1, AN. And second row is A2, A1, A2 squared, ... A2, AN, ... AN, A1, ... AN squared. Now I'm going to assume that this A1, A2, ANs are not all 0. That means as a vector, a1, a2, an is a non-zero vector. I'm going to assume that. So all the a's are not zero. If all the a's are zero, uninteresting. At least one of the a's is non-zero. Okay, so let's assume that one of the a's is non-zero. What can you say about the rank of this matrix? Any two rows are proportional. Observe that any two rows are proportional. The first row is a multiple of a1, a2, an. Second row is also a multiple of a1, a2, an. Last row is also a multiple of a1, a2, an. So the rank of the matrix is 1. So what is the nullity of the matrix? N minus 1. The nullity of the matrix is n minus 1. Rank of the matrix is 1. 0 is an eigenvalue. What is the geometric multiplicity of the eigenvalue? The geometric multiplicity of the eigenvalue 0 is n minus 1. Okay. What is the trace of the matrix a1 squared plus a2 squared plus an squared? The trace is the sum of the eigenvalues. I know that the sum of the eigenvalues lambda 1 plus lambda 2 plus dot 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 plus lambda n. I know the value of that. I know that 0 is an eigenvalue with geometric multiplicity n minus 1. So the algebraic multiplicity must be at least 0 is an eigenvalue of algebraic multiplicity at least n minus 1. But then I must have 0 as an eigenvalue counted at least n minus 1 times. So lambda 1, lambda 2, lambda n minus 1 is already 0. That is why I am saying confidently that the last eigenvalue lambda n must be exactly a1 squared plus a2 squared plus an squared. Okay. That's exactly why I'm able to say confidently that the last eigenvalue lambda n must be this. Because I know that 0 is an eigenvalue counted at least n minus 1 times. Okay. So we got a complete list of eigenvalues. What are they? 0, 0, 0, 0, n minus 1 times. So geometric multiplicity is n minus 1. The algebraic multiplicity has to be at least n minus 1. But it can't be strictly larger because it traces the sum of the eigenvalues. And we got one more. Okay. So we got the complete list of eigenvalues of A0. Now remember, if lambda 1, lambda 2, lambda n are the eigenvalues of a matrix A, then, and if G is a polynomial, what are the eigenvalues of G of A? G lambda 1, G lambda 2, G lambda n, right? We have seen that. So now let us look at, we have this matrix A0, and let us look at I plus A0. We have the list of eigenvalues of A0. We can write down the list of eigenvalues of I plus A0. What are they? Add 1 to all of them. 1, 1, 1, 1, 1, 1, n minus 1 times. So the last eigenvalue is 1 plus A1 squared plus A2 squared plus AN squared. And then what is the determinant of I plus A0? Determinant of I plus A0 is the product. Determinant of a matrix is the product of the eigenvalues, remember? So we again get determinant of I plus A0 is 1 plus A1 squared plus da 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 plus AN squared. So we have done this determinant calculation we did earlier, but now we have got it much more efficiently using eigenvalues and eigenvectors. Let us look at another exercise. A cap, B cap, C cap are 3 mutually perpendicular unit vectors in Rn. There are 3 mutually perpendicular unit vectors in Rn. I write them as columns and I create the n cross 3 matrix whose columns are A cross A cap, B cap and C cap. What is the nullity of A transpose? You see, A is a n cross 3 matrix. A transpose is a 3 cross n matrix. And the rank A cap, B cap, C cap are mutually perpendicular. They're linearly independent. So rank of A is 3. Rank of A transpose is 3. A transpose is a 3 cross n matrix. So what is the nullity of A transpose? N minus 3. So take an element in the null space. A transpose V equal to 0. If A transpose V equal to 0, AA transpose V is also equal to 0. So anything in the null space of A transpose will also be in the null space of AA transpose. So the nullity of AA transpose is at least n minus 3. Now let us try to find the eigenvectors of AA transpose. If you try to find the eigenvectors of AA transpose, suppose for example, let us calculate AA transpose of A cap. Let us calculate A transpose is a 3 cross n matrix and A cap is a column. Capital A transpose. Capital A transpose, you write down capital A transpose and you calculate capital A transpose A. And then you see what you get. You're going to get 100. Then A applied to 100 will pick up the first column of A, which is A, which is little a cap. So AA transpose applied to little a cap is again little a cap. So little a cap is an eigenvector of AA transpose with eigenvalue 1. Similarly, little b cap will be an eigenvector of AA transpose with eigenvalue 1. And little c cap will be an eigenvalue of AA transpose, will be an eigenvector with eigenvalue 1. So A cap, B cap, C cap are all eigenvectors of AA transpose with the same eigenvalue 1. That means that the geometric multiplicity of the eigenvalue 1 is at least 3. So the algebraic multiplicity is also at least 3. But 0 is already an eigenvalue with multiplicity n minus 3. So that's all that there is to it. So 0 is an eigenvalue of multiplicity exactly n minus 3 and 1 must be an eigenvalue with multiplicity exactly 3. So you completely found the list of eigenvalues of AA transpose. Once you have found the eigenvalues of AA transpose, you got your lambda 1, lambda 2, lambda n, and you've noticed that n minus 3 of them are 0. You have found that n minus 3 of them are 0 and 3 of them are 1. 1, 1, 1, 0, 0, 0, 0, so n minus 3. So now take the sum of the 3 by 3, lambda 1, lambda 2, lambda 3, lambda 2, lambda 3, lambda 4. Take 3 eigenvalues, take the product and take the sums. And you know that. What is that going to be? It is going to be the sum of the 3 by 3 principal minors of AA transpose. So find the sum of the 3 by 3 principal minors of AA transpose. What is the value? 1. What is the value? 1. On the other hand, if I take A transpose A, I get the Gramian. I get the Gramian of ABC, but the Gramian of ABC is again going to be 1. So we are seeing that determinant of A transpose A is a sum of the 3 by 3 principal minors of AA transpose. So we'll take this up. This problem will be done in detail in the next tutorial class. But I already given you some kind of hints. You have to work on it. Now let's continue with diagonalizability. Remember the theorem. When is a matrix said to be diagonalizable? If it satisfies one of the two equivalent conditions. Which are they? A has n linearly independent eigenvectors. B, there exists a non-singular matrix P such that P inverse AP is diagonal. We'll add to it one more condition. The following are equivalent, these two conditions. And the third condition is now for each eigenvalue lambda, the geometric multiplicity of lambda exactly equals the algebraic multiplicity of lambda. So we have to show that these three things are now equivalent. We already know that the algebraic multiplicity is greater than or equal to geometric multiplicity. We have to understand that equality holds if and only if if and only the equality holds if and only 1 holds. So let us prove that 1 implies 3. Assume 1. A has n linearly independent eigenvectors. So let this be. Let these be v1, v2, vn. And let us look at the list of eigenvalues. The eigenvalues may not be distinct. So that's why I had to call them lambda 1, lambda 2, lambda k. Lambda 1, lambda 2, lambda k is a list of distinct eigenvalues. Now collect all the vectors. So k could be strictly less than n. So several eigenvectors may correspond to the same eigenvalue lambda. So collect all those vectors in my bag B such that the eigenvalue corresponding to eigenvalue lambda 1. So several of them may correspond to eigenvalue lambda 1. Several of them may correspond to eigenvalue lambda 2, etc. Those which correspond to eigenvalue lambda 1, S1. Those which correspond to eigenvalue lambda 2, S2, etc. So what is gamma, little gamma 1? The geometric multiplicity of lambda 1. And that is going to be the nullity of A minus lambda 1I. Now S1 is a linearly independent subset of nullity of A minus lambda 1. The null space. So you take A minus lambda 1I and you find the null space. And if you take and every eigenvector must be an eigenvector by definition is in the null space of A minus lambda I. And I have already here a bunch of vectors which are linearly independent. And so this number of elements will be less than or equal to gamma 1, the dimension of this space. So the nullity, the cardinality of S1. S1 consists of a bunch of linearly independent elements in the nullity, in the null space. And the nullity is the dimension of the null space. And so the number of elements in S1, the number of elements in this linearly independent set S1 must be less than or equal to the dimension. So mod S1 is less than or equal to gamma 1. And the geometric multiplicity gamma 1 must be less than or equal to algebraic multiplicity alpha 1. Similarly for S2, similarly for S3. So mod Sj less than or equal to gamma j less than or equal to alpha j. Let us sum over j. If sum over j, n will be equal to summation mod Sj less than or equal to summation gamma j less than or equal to summation alpha j. But summation of alpha j is n because when I add up the algebraic multiplicities, remember what is algebraic multiplicity? The multiplicity of the eigenvalue seen as a root of the characteristic polynomial. So I have taken the roots of the characteristic polynomial, the distinct roots lambda 1, lambda 2, lambda k of the characteristic polynomial, and I'm taking their respective multiplicities. I add them up. I'm going to get the degree of the characteristic polynomial, the degree of n. The degree of the polynomial is n. Now the SJs are disjoint. The SJs are pairwise disjoint, and the total number of elements, is going to be n. So I get this inequality. These middle inequalities must actually become equalities. So you see, gamma j is always less than or equal to alpha j, and summation of gamma j happens to be equal to summation of alpha j. That means that each gamma j must compulsively be equal to alpha j. So 3 is proved. So 1 implies 3 we have proved. Now let us prove that 3 implies 1. Let us say that, let us assume that the geometric multiplicity equals the algebraic multiplicity. Geometric multiplicity is gamma j, that is the nullity of A minus lambda j. Nullity of A minus lambda j, so take a basis of the null space. Nullity is the dimension of the null space. So nullity is gamma j means there are gamma j elements in the basis. So pick vj11, vj1, vj gamma j. Take gamma j linearly independent elements here in the null space. So I have taken Sj to be a basis for the null space A minus lambda ji. And so these members of Sj are eigenvectors with eigenvalue lambda j. But these SJs, I'm going to take the union of these SJs. These SJs are going to be disjoint. These SJs are going to be pairwise disjoint. They have to be disjoint, right? Because if I take something in S1 and something in S2, there cannot be anything common between S1 and S2. But S1 consists of eigenvectors with eigenvalue lambda 1. S2 consists of eigenvectors with eigenvalue lambda 2, and lambda 1 and lambda 2 are distinct. So you can't have anything common between S1 and S2. And so the cardinality of S1 union S2 union Sk is the sum of the cardinalities. This sum of the cardinalities is gamma 1 plus gamma 2 plus gamma k. But the gamma 1 plus gamma 2 plus gamma k is the same as alpha 1 plus alpha 2 plus alpha k, because the geometric and algebraic multiplicities match. And the sum of the algebraic multiplicities is always n. And so I have, so the cardinality of S1 union Sk is exactly the dimension. Now, we will show that this S1 union S2 union Sk is linearly independent. If you show that this is linearly independent, then I got a linearly independent set consisting of eigenvectors, and the total number is n. And that's exactly what we want to show, that if you have a linearly independent set consisting of n vectors in an n-dimensional space, then it's a basis. A generating set consisting of n vectors in an n-dimensional space is a basis. Remember, right in the first week we discussed this. So we'll show that S1 union S2 union Sk is linearly independent. How to show that they're linearly independent? Suppose there exist scalars. Cj1, Cj2, Cj gamma j, and j runs from 1 to k, such that this linear combination is 0. How do we do this? How do we simplify this? Let us apply a minus lambda 2. If I apply a minus lambda 2, so what are these? The first parenthesis consists of eigenvectors with eigenvalue lambda 1. The second parenthesis will consist of eigenvectors with eigenvalue lambda 2, etc. Now, if I apply a minus lambda 2, all the elements, all the members in the second parenthesis will disappear. Similarly, if I apply a minus lambda 3, all those things in the third parenthesis will disappear. And so I'm going to apply a minus lambda 2, a minus lambda 3 in succession. So if I apply a minus lambda 2, a minus lambda 3, a minus lambda k, this should be a k, a minus lambda 2, a minus lambda 3, a minus lambda k in succession, all the things will disappear except the first parenthesis, because I'm not applying a minus lambda 1. But remember that, what happens when I apply, remember when if V is an eigenvector with eigenvalue lambda, and I apply a minus mu to V, a minus mu applied to V will be AV minus mu V, but V has eigenvalue lambda. V is an eigenvector with eigenvalue lambda, so you're going to get lambda minus mu V, So use that simple idea. So you will get, when I apply this, all these a minus lambda 2, a minus lambda 3, a minus lambda k, this n should be k here. Let me highlight it. This n should be k. I will make the correction. So if I apply a minus lambda 2, a minus lambda 3, a minus lambda k, all the things will disappear except those things in the first parenthesis. What about those things in the first parenthesis? I will get lambda 1 minus lambda 2, lambda 1 minus lambda 3, lambda 1 minus lambda k. So I'll get lambda 1 minus lambda 2, lambda 1 minus lambda k from all the terms, and I'll be left with C11, V11, C12, C etc. C1 gamma 1, V1 gamma 1. That will be left out. But the lambdas are distinct. The lambda 1, lambda 2, lambda k are distinct. So that would mean C11 V11 plus ... C1 gamma 1 V1 gamma 1 is 0. But remember that the elements of S1 were linearly independent. So these coefficients C1, C11, etc. up to C1 gamma 1, they must be individually 0. These coefficients. Okay. So that's how. So that's how I killed. That's how I showed that the first group of coefficients is 0. Similarly, you can show that the second group of coefficients is 0, etc. individually. So that will complete the proof that 3 implies 1. Yes, it's a slightly theoretical argument, it's a slightly abstract argument, but slowly you're getting the hang of it. The pattern of reasoning is slowly becoming clear to you. Gradually, we have seen this kind of argument before. Now let us prove a very important theorem called the Cayley-Hamilton theorem. If you have, and you already seen this Cayley-Hamilton theorem for 3 cross 3 matrices, etc. in your 12th standard, that if you take a n cross n matrix A, you write down the characteristic polynomial x to the power n plus c1 x to the power n minus 1 plus dot 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 plus cn. Then a to the, wherever there is x, you put a to the power n plus c1 a to the power n minus 1 plus dot 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 cn into 1. Cn into 1, you write it as cn into I. Constant term, you make it I. Cn into I. Then that's good. That matrix equation will be 0. A to the power n plus c1 a to the power n minus 1 plus dot 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 plus cn I is 0. In short, in other words, a matrix satisfies its own characteristic equation. A matrix satisfies its own characteristic equation. This is called the Cayley-Hamilton theorem. The proof of the Cayley-Hamilton theorem is not completely obvious, but we are going to prove it when A is diagonalizable. Let us assume that the matrix is diagonalizable. Okay. The complication, it's going to be easy when it's diagonalizable, but we are going to actually prove it. We are going to prove it even for a much smaller class. We are going to prove it for upper triangular matrices. We are going to prove it for upper triangular matrices right now. Okay, so I'm going to assume that A is upper triangular. That is, the diagonal entries are A11, A22, A33, dot dot dot, ANN. Entries below the diagonal are all 0, and above the diagonal it could be whatever, I don't care. The matrix is displayed in front of you. What is the characteristic equation? No prizes for guessing. A11 minus x, A22 minus x, dot dot dot, ANN minus x. So A11, A22, ANN are the eigenvalues. Upper triangular matrices are easy. So the characteristic equation is A11 minus x, A12, A22 minus x, ANN minus x. Let us show, or x minus A1. We want to make it a monic polynomial. Remember, x minus A11, x minus A22, dot dot dot, x minus ANN. We have to show that capital A minus A11 I into capital A minus A22 I dot 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 capital A minus ANN I is 0. Okay, so let us start with the last one. Capital A minus ANN. If I subtract ANN I from this, if I subtract ANN times I from this matrix, what is going to happen to the last row? The last row is going to be 0, isn't that so? The last row is obviously going to be 0. So now let us look at the product. Capital A minus ANN I, capital A minus AN minus 1, N minus 1 I. If I take a product of two matrices, B, C, and B has last row 0, C is whatever be the matrix, I don't care. The last row of the product will also be 0. So the last row of this product is 0. Because the last row of this matrix is 0, A minus ANN I. The last row of this product matrix is 0. But the factors commute. But these two factors will commute. You can check. So that means that the last row of A minus AN minus 1 N minus I, A minus ANN I is 0. This matrix has last row 0. But for this particular matrix, but for the last displayed matrix, the last two rows must be 0. The last two rows must be 0. You can multiply and check. Because when I look at this factor, A minus AN minus 1 N minus 1 I, the penultimate row must be 0. So the penultimate row of this product must be 0. But we also already seen that the ultimate row is 0. That from the previous page we got that. But from this we can also see that the second last row must also be 0. That's it. Now look at because for this particular matrix the last two rows are 0. If I throw in A minus A n minus 2 n minus 2i, for the product of these three matrices, the last two rows must be 0. B, C, D. I know that the last two rows of BC are 0. And now I put a D there. So last two rows of BCD will be 0. But if BCD commute, then I'm going to rearrange the factors. I'm going to write it as D. I'm going to write it as DBC. So I'm going to write this factor, the last factor. I'm going to write it first. So A minus A n minus 2 n minus 2i times this particular thing has last two rows 0. But this matrix has the third last row also 0. A minus n minus 2 n minus 2i has a third last row 0. And so this product will have last three rows 0. So keep proceeding like this. And so finally what do you get? When I put them all, all rows are 0. So that completes the proof of the Cayley-Hamilton theorem. For which case we have proved the Cayley-Hamilton theorem for upper triangular matrices only. Now you will say, what's the big deal? You proved the Cayley-Hamilton theorem for upper triangular matrices. You will say that, well, you couldn't prove it in the general case. So you conveniently proved it for a special case, and you try to wriggle out of the complication. No. We are going to use this special case to prove the general case. The special case of the upper triangular matrix will be a springboard to go to the general case. Now, suppose if P is a non-singular matrix, and if Q is a polynomial, suppose if P is non-singular, and I calculate P inverse AP. P inverse AP squared will be P inverse AP, P inverse AP, that will become P inverse A squared P. P inverse AP cube will be P inverse A cube P, etc. So if Q is a polynomial, then Q of P inverse AP will be P inverse of QAP. You have checked it for polynomial Q of x equal to x squared, x cube, etc. You can take linear combinations of x squared, x cube, and you can check that for any polynomial Q, Q of P inverse AP is going to be P inverse times QAP. Now, we are going to prove later that given any matrix whatsoever, I can find a matrix P such that P inverse AP is upper triangular. I can find a matrix P such that P inverse AP is upper triangular, and P inverse AP and A have the same characteristic polynomial. P inverse similar matrices have the same characteristic polynomial, and for P inverse and for the upper triangular matrices, I have proved that this satisfies. So Q of P inverse AP is 0. Therefore, Q of A must be 0. Similar matrices have the same characteristic polynomial. So once we prove that every matrix is similar to an upper triangular matrix, our job will be over. So we have proved it for a special case, but that special case will serve as a springboard for the general case. And we shall stop this lecture here.